Significant figures in calculations. To determine the appropriate number of significant figures in the answer to a calculation, we consider only measured numbers. Exact numbers, as discussed earlier, do not affect significant figures. The final answer should always be reported with only one uncertain digit. Multiplication and division. In multiplication or division, the result must have the same number of significant figures as the least precise number in the calculation. Consider the following example. The first number has 2 significant figures, while the second has 3. The answer must have 2 significant figures, matching the least precise number. Addition and subtraction. For addition or subtraction, the result can only be as precise as the least precise number in terms of decimal places.
Consider the example.
The addition gives 1.05122023. The least precise number, 1.0506, has 4 decimal places. So, the answer must also have 4 decimal places, 1.0512. The result has 5 significant figures. Calculations involving multiple steps. When performing calculations with multiple steps, it's crucial to track the number of significant figures and intermediate results. To minimize rounding errors, avoid rounding until the final step. As an example, consider the 2-step calculation. Perform calculations following the order of operations. Parentheses have the highest precedence, followed by multiplication and division, and finally addition and subtraction. So, first perform the subtraction 21.62 to 11.7, which gives 9.92. According to the significant figure rules, the result should have 1 decimal place. Because 11.7 has the fewest decimal places, the result should have 2 significant figures. Then perform division, 9.92 divided by 3.98. That yields 2.49246, 23115577895. The numerator has 2 significant figures, while the denominator has 3. The final result must have 2 significant figures. So, after rounding, the final result is 2.5. Rounding off numbers. When rounding off numbers, we drop the digits after the last significant figure, using the following procedure. 1. If the first digit being dropped is less than 5, leave the last significant figure unchanged. Example, rounding to 3 significant figures, 9.063 becomes 9.06. 2. If the first digit being dropped is greater than 5, or if it is 5 followed by digits other than 0, increase the last significant figure by 1 unit. Example, rounding to 3 significant figures, 9.067 becomes 9.07. 3. If the first digit being dropped is exactly 5, followed only by zeros or no other digits, there are multiple rounding methods. We will use the rounding half-up method as our standard approach. In this method, if the first digit being dropped is 5 or greater, increase the preceding digit by 1. Example, 4.050, rounding to the first decimal place, becomes 4.1. Another example, minus 6.995, rounding to the second decimal place, becomes minus 7.00. Significant figures and common logarithms. Let's consider a measured value, say 47.6, and calculate its base 10 logarithm. If you plug this into a calculator, you'll see a result like this, 1.6776, etc. That's a lot of digits. But here's the thing, the original value, 47.6, has 3 significant figures. So, the logarithmic result must be rounded accordingly. Now, here's a common pitfall. If you think the rounded result is 1.68, you'd be wrong.
Surprised?
Let's dig deeper into why that's the case. First, let's quickly revisit some properties of logarithmic functions to set the stage. Look at the graph of log x. When x is between 0 and 1, log x is negative. When x is between 1 and 10, log x falls between 0 and 1. It's a fractional value. And for x greater than 10, log x is greater than 1. Another important property of logarithms is the product property, which says that for any two positive numbers a and b, log ab equals log a plus log b. Let's rewrite 47.6 in scientific notation and use that. Log 47.6 equals log 4.76 by 10 to the 1. Applying the product property, this becomes log 47.6 equals log 4.76 plus log 10 to the 1. Since log 10 to the 1 equals 1,
we get
log 47.6 equals 1 plus log 4.76. Notice something critical here. The integer part of the result, the 1, comes from the exponent of 10 in the original number. It's not affected by significant figures. It's the fractional part of the logarithmic result that must match the significant figures of the original value.
Now,
log 4.76 equals 0.6776, etc., and rounding this to three significant figures gives 0.678. Adding the integer part back in, we get log 47.6 equals 1.678. So, the correctly rounded logarithmic value is 1.678, not 1.68. To summarize, when taking the common logarithm of a measured quantity, the number of digits after the decimal point must equal the number of significant figures in the original number. Antilogarithms. Let's talk about antilogarithms, which are the reverse of taking a logarithm. If you're given y equals log 10x, then the antilogarithm brings you back to the original value. X equals 10 raised to the power of y. Now, let's revisit the example from earlier. We calculated log 10, 47.6 equals 1.678. To find the antilogarithm, we simply calculate 10 to the 1.678. Punch it into your calculator, and you'll get 10 to the 1.678 is equal to 47.643, etc. The original value, 47.6, had three significant figures, so the antilogarithm must also be rounded to three significant figures. When we do that, we recover the original value, 47.6. And there you have it. The antilogarithm brings us right back to where we started, as it should. Additional example.